All, welcome back to the tutorials on Arduino. We will continue our discussion on various features of Arduino Uno boards. So the first thing we will talk here is about the interrupt pins on the Arduino board. So Arduino supports two external interrupts on its pins. So those are basically a circle here, INT0 and INT1. Other than this, there are other pins that support interrupts, but these interrupts basically are something where when an interrupt occurs directly, the interrupt service routine gets called and it gets serviced. Whereas on the GPIO pins, the Arduino Uno supports something called pin change interrupts, which all those pins PCINT0 to PCINT23, all of the pins support this pin change interrupt. So what is basically pin change interrupt is and how it is different from external interrupt. So it is very important we need to know that. So in the external interrupt, what happens is once you have the interrupt on a particular pin, that means there is a level change, automatically the firmware gets routed to the specific interrupt service routine and then the instructions get executed. Whereas in the pin change interrupt, it is the firmware engineer who has to write the code on which pin it has changed. The firmware engineer has to read and then invoke the respective ISR. So there is a lot of difference, right? The hardware automatically raising an interrupt and then going to ISR, whereas firmware required to read the state and then invoke the ISR. So there is a clear difference between the interrupts, the two interrupts which we talked here, INT0, INT1, and then the pin change interrupts. And apart from the interrupts, one of the important features supported on Arduino Uno is the analog. So we have talked about that in our initial videos. We said Arduino Uno supports analog inputs. So if you see the 80 mega 328p microcontroller, basically the pins PC0 to PC5, that means total of 6 pins, support the analog functionality. So the same pins which are PC0 to PC5 are pulled to the specific connector and are named as A0 to A5. So any of these pins can be used for analog functionalities. You can see here analog in. So if you want to connect an analog sensor, example like a temperature sensor, you want to read which provides analog output. So you can connect to the pin and you can internally process those analog inputs. So this analog input, once it is read by the microcontroller, internally there must be some block which takes care of processing this analog signal and converting it to a digital signal, because the microcontroller, we know, right, it's a digital thing. All the operations happen with respect to digital, it's not the analog. So this analog need to be converted to digital, which is done by analog to digital converter, which is present inside 80 mega 328p microcontroller. And this ADC is a successive approximation type. So successive approximation type is one of the common ADCs used, and if you take any microcontrollers, it is the one that is used. So we will see because while we read about it, we also need to know what is a successive approximation, why successive approximation is used. We need to know, right? So let us talk about the successive approximation ADC. So three major advantages which drive successive approximation ADC being used in microcontrollers are the low power consumption that is there with the success approximation, and specifically low cost to implement the blocks, and then sufficient resolution, which is enough for a microcontroller related functionality for for reading the external sensors. So, considering all these, if you take any microcontroller in the world, you can see that mostly they use success approximation type ADC. So this is the basic block. So there are two things here. While we will just touch the approximation at a very high level. So Vn is basically the analog input, so which will be given to a sample and hold circuit and post. So sample and hold, which itself tells that you are going to sample, you are going, and then you are going to hold. So this is a standard circuit, and then the sample and hold circuit is given to the input of a comparator, to the positive terminal of a comparator, and then to the other end of the comparator we give a DAC output. So this DAC output, initially it will be at a specific level, and based on the comparison with respect to the input, so this produces the control signal to this SAR ADC, and then successively the bits get changed, and again it gets converted to analog by the DAC. So three things here. One is basically the DAC output, the performance of the DAC, and the success approximation register type, where the output is depending on the comparator stage. So these two are the very, very important points that we need to remember in success approximation. It's a little advanced ADC conversion other than the normal ADCs, simple ADCs which are there. So, and then this is basically how the muxing happens inside the ADC. What do you mean by muxing? So, in the slide, we said there are 5 analog inputs, right? And then we said for each of these input, we need an internal ADC to process these analog pins. So does it mean there are 6 ADCs inside the 80 mega 328P? No, it's not that way. So generally, if you take the ADC inside a microcontroller, right, it will be a single unit, and based on the inputs that are there, they will be provided to a mux, and then that mux output, the single output, will be given to the ADC that is present inside. So now, if you see the block diagram of this is a block diagram of ADC section inside 80 mega 328P microcontroller. So you can see here there is an input mux, and all the ADC pins are connected to the mux, and then this mux output is further given to the respective sections of the ADC. So you can see here there is a comparator. We have given this V in to this sample and hold circuit, and then this will be given to the SAR register, where it converts it into a digital value, and digital value will be given to a DAC, which again gives a output. So again the success approximation register. And then another important point we have to remember is, for the ADC to work in any scenario, any microcontroller or anything, the important point is the reference. So the reference is the voltage against which this microcontroller operation depends on, and the reference in 80 mega 328P for a given ADC is selectable. So you can see here these are the ADC pins. So if you go to the slide, you can see here the 3 things which are marked in red: AVCC, A reference, and internal 1 volt reference. So if you can see, either of these 3 goes to a DAC as a V reference input. So the maximum voltage that you can use this particular ADC. So what do you mean by maximum voltage is the maximum input voltage that can be read by this ADC depends on the VREF. So beyond VREF, if you give any voltage, it will be erroneous value that will be read by the microcontroller. So the reference voltage is very important, and the reference voltage has to be stable. So a very important point to remember while working on ADCs. So this, while we talk about Arduino, we have been mentioning in our videos these basic important things are applicable to any of the microcontrollers. So if you understand one microcontroller, you can get to know or easily understand the other microcontroller architectures as well. Hope we were able to give some information to you on some of the features of Arduino. We will continue our discussion on the next videos. Please post if you have any comments. Please let us know your suggestions on our videos. Thank you.